Bad retrieval often starts before the vector database. Add context to each chunk before embedding, and your RAG system can retrieve meaning instead of fragments. This is the pattern you'll be able to implement by the end, which enriches chunks with section context and retrieves the best evidence for a question. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Context first. When you build a retrieval augmented generation system, you usually split documents into chunks, embed them, and search. The common pain is that fixed chunks lose the document structure. You get fragments that look plausible but sit in the wrong section. The result is hallucination or weak answers. Success means the retrieved chunk carries enough intent and placement to support the model answering correctly. Intuitively, we want each chunk to carry a short note of where it came from. Think of a manual with sections named Intro, Install, and Usage. If a chunk says Install in front of it, Retrieval knows that similar words in the install area are more likely to answer setup questions. This reduces ambiguity and boosts the chance that the top hit contains the right evidence. We will build a tiny example that walks from naive chunks to section-aware prefixes, measure simple query coverage, add intent tags, and finally run a minimal embedding retriever to see the effect. The code will be tiny and deterministic, so you feel the effect at each step. Now we will create a tiny document and split it into naive chunks. This snippet builds a tiny document and splits it into naive chunks. The variable docs text holds 3 short sections, while SplitSense turns the text into sentences by removing new lines and splitting on periods. The function makeChunks groups sentences by a fixed size of 2, losing any notion of titles or sections. The variable naive chunks collects these units, and Avg computes a quick length average to show chunk granularity. Fixed size grouping is fast but blind to context, which is why many RAG systems return fragments that feel detached from their original sections. The printed values confirm how many chunks were created and how large they are. Next, we will attach section labels to each chunk, so they carry location info. This example adds compact, chunk-level context by prefixing each chunk with its section. The variable labs tracks the current section by reading the sentence head before a colon, updating when it sees intro, install, or usage. The list chunks CTX is then built by combining a 2-sentence body with a concise prefix of the form title, get section. The variable pre extracts the first prefix, and n counts how many distinct section tags appear across chunks. With section-aligned labels, each chunk now carries intent and placement, which helps Retrieval later disambiguate similar wording across different parts. The printed values verify that 3 unique context tags were added and show an example prefix. Now we will compare simple overlap recall between naive and contextual chunks for a targeted query. This snippet compares retrieval quality by computing query term recall over 2 chunk sets. The function toke converts text to lowercase word tokens using Python RE, returning a set for simple overlap checks. The function topCover evaluates each candidate's fraction of query words covered, then returns the maximum score for the set. The variable Q contains a targeted query with words that should benefit from context labels. Because chunks_TTX includes the section-aware prefix containing the word guide, the coverage for contextual chunks can reach full recall, while naive chunks typically miss that extra signal. The printed scores show how adding section context directly improves per chunk query coverage. Next, we will add short intent tags that normalize synonyms across sections. This snippet augments chunk prefixes with short intent tags that normalize wording. The dictionary intents maps section names to a compact label like setup for install. The function add tags reads each chunk section from its prefix and appends an intent token when available. The variable ctx tagged holds the enhanced chunks that now match broader synonyms. Using top cover again with the query setup guide highlights how intent tags recover meaning even when the original body lacks that synonym. If you expand or shrink the intents mapping, you will capture more or fewer paraphrases, directly changing the recall you observe. The printed scores show the gain from adding intent-aware context. Now we will embed the intent tag chunks with a tiny deterministic vectorizer and rank by similarity. This code builds a minimal embedding-based retriever and applies it to the intent tag chunks. The function embed creates a deterministic vector by hashing each token with hashlib.md5, bucketing into a small fixed dimension, and L2 normalizing the result. The variables ems and q hold the normalized vectors for chunks and the query. The list sims computes cosine similarity as a dot product because all vectors are already unit length. Finally, I selects the highest scoring chunk index. Increasing the dimension d reduces collisions but costs memory, while smaller d is faster but blurrier. The printed cosine and index confirm which enriched chunk would be returned first and how strongly it matches. This tiny run maps cleanly to a real project. Replace the toy embedder with a production model and the same steps still apply. Prefixes and intent tags scale to large manuals, API docs, or product knowledge bases and improve the signal that embeddings capture. Recap what it is. It is a simple pattern that adds section and intent context to chunks before embedding to boast retrieval relevance. When to use it. Use this when documents have clear sections and you need higher precision from top hits, like troubleshooting guides or API docs. One caveat. Overly long prefixes can pollute embeddings, so keep context concise and focused. Next step. Tune the embedding dimension for your production model or index, so you trade off collisions and memory. Increase dimension d to reduce hash collisions, or use an approximate nearest neighbor index to scale. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.